Okay. I will, it will work hopefully from now on. They didn't tell you that, they didn't tell me that I had to update the software. So it wouldn't work. So I updated the software this morning, and now it's working away. So hopefully we'll have no other problems, and if it comes up, I will be sure to check whether there's a software update. Okay, so I want to go through these 7 problems, but before we get there, so there's we're going to move on to one more concept towards the end of class today, and the relationship between saying that something has connectivity. My G's look like capitals. My K's look like. So connectivity of G. So versus G being K connected. And I want to start out with, this jumps into the next section, but just to give you an idea of the flavor of the difference. When I say that G is K connected, when I say that G is K connected, and does he use hyphen? He does. Okay, what that means is that the removal of fewer than K vertices, the removal of fewer than K vertices leaves a connected graph. So for any set, if I say the graph is K connected, for example, let's look at 2 connected. If I say that the graph is 2 connected, that means the removal of any vertex leaves a connected graph. It doesn't mean, this doesn't mean that the connectivity, let me make this clear. No, the connectivity doesn't necessarily equal K. Okay? But it means that the connectivity is at least K. One more time, the removal of any set of fewer than K vertices leaves a connected graph. So if I was going to disconnect the graph, I would have to remove more than K minus 1 vertices. So we know that the connectivity is at least K, but we don't know that it is exactly K. So again, there's 2 different terms, and they kind of sound the same, and the words come out the same. So we can say that a graph is K connected, which means that the removal of fewer than K vertices leaves a connected graph. And we can say that a graph has connectivity K, which means that there is a set of K vertices whose removal disconnects the graph. So one more time. To say that it's connectivity, to say that a graph it has connectivity equal to K means that this parameter is equal to K, meaning that there is exactly a set of K vertices that disconnects the graph, and no fewer, no smaller set disconnects. Okay, is it clear the difference between saying that a graph has connectivity K and is K connected? Okay, so we'll do a couple problems with. Let me start. Let's just jump right over to W6. So that's on page 245. I wouldn't say that this is standard notation, but this is standard notation in his book, in their book. the wheel on 6 vertices. The wheel on 6 vertices. So the tire has 5 vertices, and the hub, I don't know, what's in the middle of a wheel?
Center.
The center?
Yes.
Okay, the center has 1 vertex. Okay, so this is called W6. Okay, it's the wheel on 6 vertices. It is one connected. By the way, we abbreviate one connected by saying connected. It is one connected because if I remove any one vertex, I leave a connected graph. Okay, so this is one connected. Okay, so I'm looking at these problems here on page 245. Is it right to say that G is 2 connected? So what would that mean? Before you just say yes or no, what would that mean? Okay, what would it mean to say that W6 is 2 connected?
Is it the removal of any 2 vertices leaves a connected graph?
That's exactly what it means. Being K-connected means the removal of fewer than K vertices leaves a connected graph. So if I remove 1 or 2 vertices, is the graph connected?
Yeah,
Okay, so it is 1
yes,
connected.
is 2 connected.
It is 2 connected. Is it 3 connected? It is 3 connected. The removal of fewer than 3 vertices. The removal of, sorry, I didn't know if you were looking around. The removal of fewer than 3 vertices leaves a connected graph.
So
Sorry.
not less than or equal to,
It's
just less
right,
than.
strictly less than. So one more time. So to say that a graph is K-connected means that the removal of fewer than K vertices leaves a connected graph. It doesn't mean that if I remove K vertices, the graph is disconnected. Okay? So this graph it's connected. It's 2 connected. It's 3 connected. The removal of fewer than 3 vertices. Is it 4 connected?
No.
It's not 4 connected. Okay, but it is 3 connected. So I can then say, so IV, so part IV is no. And then we also know that the connectivity of G, the smallest set of vertices that disconnects this graph, is equal to 3.
What was the last sentence you said?
The smallest set of vertices that disconnects this graph is equal to 3. So can you give me a set of 3 vertices that disconnects this graph?
The top, the middle, and any bottom.
The top, the middle, the top, the middle, the top, the middle, and any one at the bottom, you say. The removal of those 3 vertices disconnects this graph. Okay? So one more time, it's not 4 connected because there is a set smaller than 4 that disconnects the graph. Okay, it is 3 connected because the removal of fewer than 3 vertices doesn't disconnect the graph. And that's the cutting point on when I can actually define this parameter, the connectivity of G. Okay? For, wait a second. So W6 is 1 connector. The removal of fewer than 1 vertices. The removal of fewer than 1 vertex. How many is less than 1 vertex? 0. So if I remove 0 vertices, is the graph connected? Yeah. So all the which graphs? All the connected graphs are 1 connected. Okay? All connected graphs are 1 connection. Okay? That doesn't mean that they have connectivity 1, right? Because here is a connected graph, here is a connected graph, here is a connected graph that doesn't, its connectivity is 3. It is 1 connected, it is 2 connected, it is 3 connected. Okay, and the connectivity is equal to 3, because it's not or connected. Okay, those words, kappa of G is the parameter, kappa of G is the parameter, and connectivity just tells you a little bit, you're not being, you don't have to be exact. When I say exact, optimal. Again, to say that that's connected, means that the removal of fewer than one vertex leaves a connected graph. In other words, it's connected. Okay? Is that clear? It's kind of an interesting difference between using the terminology connectivity when you actually find cap of G versus 1, 2, 3, or K connected. Okay. Okay. So what I want to do is I want to look through. I want to do 1 through 7, 1 through 6 first, and then we'll talk about 7. So if you spend some time looking at these, we talked a little bit about them on Thursday. There was no tape. There was no video. There is a video that will be today. Okay, so talk amongst yourselves or tell me which one you want to do. When I say that, I mean which one you want to do.
We're constructing. Get stuff. See, we can have a minimum of this. I'm trying to construct something.
对，
And it's gonna be a huge curve, but a minimum.
Yeah, it can be. Typically, yes, in these kind of situations. Yeah,
Okay,
but
so
it's easier to think of like
I'm saying,
from the middle out in a way, right?
so it's G
Gonna
is
be
K
K, it's gotta be
connected,
2.
then its connectivity is at
Throw an
least
extra edge in there.
K.
Okay,
Yeah,
it's not
okay.
1, right?
And if G is
So
K
this
connected
makes
and it's
M&M
not
pretty
K
easy.
plus 1 connected, then its connectivity K.
Now you have
Does that sound right?
4
That sounds right.
connected.
Okay, cool,
So maybe
thanks.
there's 4 edges that go in this group.
I mean, the problem is that those words sound kind
Right.
of K connected versus connectivity K.
Right.
They gotta be the same.
Yeah.
But they're not. Okay.
Yeah.
And it's just because if it's 4 connected, it's also 1, 2, and 3 connected. That's why they're
Exactly.
opposite. If we defined the K as the max of those numbers, then they would be the same.
Then they would be the same.
Cool,
Right.
that makes
And
sense.
that's really important
Well, it's
as
not
you start to
necessarily
look at these
anything.
problems.
You know, you
We're
wanna have
gonna
at least
we're gonna be looking at graphs that are, say, 2 connected. That doesn't mean that
You
it
don't want
has
the connectivity problems
connectivity
to
too.
happen
Right.
here. You
Okay,
don't want
we
them here,
just
you
know
want
that
them
I
in
can't
the middle.
remove fewer than 2 vertices in disconnected graph. It doesn't also mean that I can remove 2 vertices in disconnected graph.
Right,
because it could still be K connected.
And actually,
cool,
if you didn't
yeah,
have this
exactly, yeah.
middle vertex, then you would just
Awesome.
have 4
Makes
for
sense.
sure edge. 4 edges deep. So
How you doing on these? You got them all
Say
done?
that one more time, if I didn't know.
if you decided not to go with this metal edge here, for some reason, it's not, but to make a more general graph like this, then you could just have 1 extra edge for each. So now there's 4 coming out of this, 4 coming out of this.
Okay, so we have. So if I take these 2 out, it's disconnected. Remove these 4, it's disconnected. And I've got minimum degree cells. Okay.
And you might want to make sure that there's no way to remove fewer.
And he mentioned that to me earlier.
So, you know that every vertex over here is, maybe this is a K.
Thank you.
For example, so deleting any
You
vertex
think
over
so?
here doesn't really change anything. Deleting 2 vertices over here doesn't change anything.
Vicky?
So deleting 2 vertices over here, maybe this is a K4 or something. Maybe you want it bigger than that just because, if you delete one of the K4,
Yeah.
and I'm saying 4 because I have 4 edges anyway. I don't want to go over this.
Sarah? Just make sure you don't have only one.
So
Only take one. Connor?
K4, I'm slightly worried about because
Ying,
Nice. Check it out. They started with Disney Dale's one, and then
It's like, oh wait, no.
yeah.
Rui,
I think something's.
Rui
If
Zhang.
they're small enough that reading stuff inside of here might cause a problem. So yeah, it still wouldn't be a problem though. Yeah, having complete graphs on either side
Summer?
and then making sure that each edge goes to a vertex.
So do I need to state that both of these parts are complete graphs?
Zhang Wen Lu,
Because if they're just paths or something like that,
Then removal of an edge would disconnect that.
Jin Wen,
right, I mean, if they're not connected to each other at all, and it just look like this. Oops. You're
Yang Cheng,
disconnected, so it would be one, right? So you need at least this edge. And an edge over here. So you need at least these edges to make sure that it's not disconnected. However, in this case, you might take
But it
these
was
two.
a K3, so I need.
Jin Yan Yu,
It can't be a K3 because there's 4 edges coming.
Right, a K3,
Isn't it?
Jia,
you could, yeah, so if it was a K3, right, these are your two in the middle,
Kichi Shen,
you did something like,
Oh,
when they overlap on this
Yu Yan
edge,
Gao?
on this vertex right here. Well,
Dylan,
here's 3 edges that disconnect. So you need the graph on this side to be at least 3 edge connected, so that when you add these edges, it's at least 4.
Thank you.
okay, now we got some old papers.
That has to be,
If you turned in homework and didn't get it, let me know.
or do
Yeah.
I?
I would say-
Jin Wen,
Like what, so what happens in a K4 is
This is the
you
test.
notice that each of these vertices has degree, which means that it's a large connector. Actually, degree 4, that's bad,
Allison,
right? It's gotta be degree 6. So,
So this has to be at least a K6.
yes, actually K7.
K7. Both of them.
It's a good thing we got that. Could've
Jin
been
Wen.
fantastic. You just imagine the implications, yeah.
Sarah would be able to do
Lu, Jin Wen,
But see, to
Lu,
note it's
Jin,
doing all that extra stuff, I would do that.
no, okay.
You think there's number 2 yet?
No, just the first one.
Allison's not here.
Which, I think I managed, but kind of complicated sort of way.
I was gonna send,
Xijia, oh my, Yanhui Wang, Jinwan Liu,
okay, so did you finish the first one?
no?
I don't have the right min degree. So it's supposed to be N7, right? So you need 7 vertices.
That's different than Jin Wen. This is Jin Yan.
Yeah, I don't know how it works out with.
Okay. They'll get it. Okay, I'm assuming everybody who handed something in got something back. Okay, how you doing?
Because that's what it's trying to.
Not good? Ying, not good? Okay, who wants to, let's start with number 1. Well, the problem is, I want a graph with min degree 2. What else do I want? I want connectivity 4. Do I? Min degree 6. Min degree 6. Connectivity is,
You could have also
let's do it this way.
like 2 K7s, so that you can.
2, 4,
And
and
there's
6.
that stuff to the middle that you can use.
Okay, so the min degree 6, let's start with that. How am I gonna, what should I do to assure that I've got min degree
Just in
6?
reverse.
Just one vertex? But I need min degree 6. So every vertex has to have 6 edges of it. Anybody?
Draw two complete graphs with 6 degrees. Draw two.
No. You had it right, but more than 6.
Draw two components
With, okay, so if I take a K6, so I think you're saying take a K6. But what's the degree of what's the degree of every vertex in a K6?
is that
Okay, so let's start with 2 K7s.
You're good.
Okay, I'm almost done. Okay, so now I want to have, so I need to have vertex connectivity 2 and edge connectivity 4. Vertex connectivity 2 and edge connectivity 4. So let's see, I want to, on one of these, I want to have 2 vertices, and on one of these, I want to have 4 vertices. So let's see, I have, so if I have, so that's too many edges, right? If I look at this graph, I have connectivity 2, vertex connectivity 2, but how many edges do I have to remove to disconnect this graph? Oh, yeah, a lot. Okay, so that's just too many. Okay, so let's come back here. So I still have 4 vertices and 2 vertices. Okay, you understand, these are part of the K7, so there's 5 more vertices here. I'm not going to draw all the edges in, and 3 more vertices here. So I'd like those 2 vertices to cut the graph. I'd like those 2 vertices to cut the graph, and I would like to find 4 edges from these vertices here to cut the graph. So what if I go like this? Let's try this again. What if I go like that? So can I disconnect the graph by just removing 2 edges? Let me back up. Can I disconnect the graph by removing 1 edge?
No.
Can I disconnect the graph by removing 2 edges? Yes? I'm putting words in your mouth. Okay, can I disconnect the graph by removing 1 vertex? Can I disconnect this graph by removing 2 vertices? What 2 vertices? The 2 on the left-hand side. Okay, so if I remove those 2 vertices, the graph is disconnected. Can I disconnect this graph by removing 4 edges?
Yes.
Let me back up. Can I disconnect this graph by removing 3 edges? Okay, and that's something you need to think about how you might show that. But if I remove all 4 edges, then I would disconnect this graph. So this graph has connectivity, connectivity 2, edge connectivity 4, and min degree 6. And we know that this inequality goes like that. So now I want you to let's do some more. Let's do another possibility. So we'll do this one in blue. No, I won't. I'll do it in black. Okay, so give me three different numbers. Smallest one. Smallest one, 1. Okay. Next biggest one. Interesting. Who's saying this? No, come on, let's make it interesting. 1's too small. Let's say 3, 5, and 8. So I want you to find a graph that has min degree 8, edge connectivity 5, and vertex connectivity 3. And again, that's what the theorem said. The theorem says if kappa is less than or equal to kappa prime is less than or equal to delta, there's a graph that has connectivity kappa, edge connectivity kappa prime, min degree delta. We're doing the black ones. We're doing 3, 5, and 8.
So, this one actually doesn't work. It's because you need the edge connectivity to be at 5. Right, so removing these 5 edges doesn't disconnect. So the way that he did it, is and then just kind of cut out and connect. Yeah. Is that right? And then do a bipartite. Does that make sense? It's a lot more general. The problem with the way that I did it is that the number of edges coming out of the middle needs to start getting worked.
不过其实右边的话也不少于3个，就是连着的点，如果少于3个的话，那就可以，对，这是右边的点，然后就是让两边都是最小的那个，不要那个我觉得是，还有一个地方就是他刚才说什么 K 小必须要 K 大，是吗？
Yeah, I would have run into a problem with that.
In general terms, not on that one.
Maybe this one might have worked because what you wanted to end up with was like 5 edges total. So like 1, 2, 3, 4, 5 going to one side and then the rest coming in. But 3 times 8 is 24. So minus 5, there's like 19 edges that come out of here going this way. You can't have 2 edges going in the same vertex. So.
Okay, so what am I going to do to get min degree 8?
Just gotta be 6 coming out.
Take 2 K9s.
So it might have barely, but it would have been close.
Here's this is K9 and this is K9.
Bigger and bigger and bigger, it starts
Okay.
getting crazy.
I want, let's see, I want edge connectivity 5, vertex connectivity 2. So let's see, if I take 2 vertices over here, want 3 over here? Oh, 3, sorry, 3. I take 3 vertices over here, and I'll take 5 vertices over here. 1, 2, 3, 4, 5. So I want to be able to remove 5 edges and disconnect the graph. So I want 5 edges between these. So where is the 3-element vertex cut? The 3 vertices that cut the graph?
5 edges total, that's
On the left, the 5 edges that cut the graph. Those are the ones in the middle, between the two. And what's the minimum degree? 8. Okay? Is that clear? I mean, and in fact, this result that we talked about a week ago, if I have for any k strictly, less than or equal to k prime, less than or equal to delta. If I take any k prime, and delta, then I can find a graph that has vertex connectivity kappa, edge connectivity kappa prime, and min degree delta. And it's essentially this proof. It's this construction. So notice I took, in this case, I took kappa vertices here, kappa prime vertices here, and I took, to make the min degree, in this case 8, I took a k9. Okay, and that assures that I have min degree. Okay? All right. Questions about that? By the way, there's lots, this is not unique, right? We could have done this in lots of different ways. Okay, number 2, let G be a graph with min degree at least 3. Show that kappa is equal to kappa prime. Sorry, max degree less than or equal to 3. I had everything wrong there. Let G be a graph with max degree less than or equal to 3. Show that the connectivity is equal to the edge connectivity.
Two examples to get myself started, so. So the maximum degree is
So kappa prime are at most 3.
Right.
because
The Peterson
You
graph.
know this one?
No, that's about as far as I've got.
You wanna see what I did, or do you wanna? Wait, so we got possibilities. Kappa can be 0, 1, 2, or 3. Right. Okay. So if it's zeros, then the graph is disconnected.
There's a vertex.
And then kappa prime is also 0. Okay. If it's 3,
The graph is
then kappa prime has to be 3 because it has to be sandwiched in between that and the minimum degree. So then they're equal. So let me just have 1 and 2 left. Okay, and I'll do proof by picture. But it would look like this. There would be something up here with stuff going on, something up here with stuff
So
going
this is
on,
what it
and then
looks
you have
like,
this.
right?
But it has a maximum degree of 3. So therefore, our edge,
Maximum degree 3.
our kappa prime is 1.
意味着这个点它的底位是
I haven't drawn any edges.
Well, no, 1, because you can remove
Oh,
this
yeah,
edge,
definitely.
and you're disconnected.
So
Yes, that makes
2
sense.
to 1,
Yeah.
1 to 3.
Okay.
Okay, and then the other possibility is that it's 2, and, our edge is, kappa prime is 2. If you want, you could draw it like this,
你可以一个点
and you still see that kappa prime is still 2. Yeah. So I know
Okay.
there's no question.
there's 3 edges.
But like just together.
That's why.
Okay.
One of them's gonna have 1.
This is, I'm trying to work
So
on number
that's
3.
a cut edge, which means it's a edge. So that's the 1 case. The 2 cases is more complicated.
And note, there's 2 parts to this.
只要
First part is to show that, the first part is, this is true,
Is greater
and the second part is to show that you can't make it, you can't look at a graph
Well, this is
with max degree
than prove what you said.
4 or more.
So in general,
And here's what
if we just take this example and show that
Because kappa
equality holds,
is
we
2,
don't have to look at it.
kappa prime is 4.
Okay, because usually then I would have
Well,
to say, well, what if it
yeah,
was just one
simpler you could
connected
say
like this, then it's just a vertex.
Here, kappa would be
Because of this.
Yeah, 1, 4. Yeah, even
and
better.
then
Even better.
So,
or 2 rather,
to,
but still different.
Yeah.
how can the edges look?
Still better.
我们只要证明 K 里边大
So
于
each of those could look like the one you previously did.
K 就
So
Oh,
they
no,
could-
because it needs to total. No. Each of those vertices, yeah, so 2 to 1, 1 to the other. Same forward.
Sure, but you could go this way.
No.
So how is that 2 edge connected?
这也是
These 2 edges.
认知小的，这是小的，
So this isn't the only one that's 2. Right, there's no edge here. So what if you had the edge? Now what does that look like?
它就是 I。 你要小心，在另外我们谈的 bias。
And we want it to be 2 edge connected.
Can the max add, yes.
Okay, so we didn't say the
Yeah.
elements. Because I could take these two. No, I could take these two.
但是你想，万一有一个点在这儿，万一有这么一个单独的点
And so what if it wasn't really like that, but instead, you had
对啊
two
，K 就
going
可以
in
等
one
于
direction. And then
这个东西适用的是它的
this,
哪个最相
or
对
like
的？
this.
这个 K 的是我们
So
刚
there's
说
a
的
whack
是
ton of
K 砍
cases
来 K 的
here to look out for.
等等，这是 K 砍来 K 的吗？还是 KG？
KG
对，我们说 KG 的时候，应该指的是它的
And
最
then
小
the
值，
other, yeah, if it looked
哦
like
对
that,
对吧？所以
it would be these two,
KG 可
or
以
these two.
如果那样的话
Right.
，KG 可以等
This
于
third edge was over
那它就
here. His degree.
那就不对了。为什么？
But it would be this one and one of these.
等于3的话，
等等啊，对，直接
And
申请
same
讨
if
论
it。looked
它
like,
只是让你看
actually, if it looked like this,
不一定说它一定要等于3。
嗯，
是的，
你像你这种情况，
对，这正好就等于一，
对对
没错。
对
然后二的时候，肯定也等于
what's this? So
正好
that's
也
one
等
edge
于
connected.
看掉。
So that sums up, right?
如果它等于1的话，那它正好等于这个情况解决。如果它等于2的话，它等于3两种情况。如果它等于2的话，
Well, the problem here is that this is actually only one vertex connected.
你能想到这个情况证明
So it still equals, as it should. You don't actually need to acknowledge this case because
你说假设
it
是
was
它是它的
taken care of here too.
Okay, because they're both 1.
Right, this is a one vertex connected graph.
And
Right, but in this case, we were supposed to be looking at two vertex graphs.
and then we need to look at 3.
它们必要每个底部都有。
Except I need to get caught up. So we have to connect
不是，是个 I 值是参数条件好吧？不是那个底部，我们要求的底部一定要小于，对，还真找不出来。何止和逆何止，到了一半就不行了。
So here cell connected to the so this would mean
这怎么证啊？
say he goes just this way. So he goes this way. So he does 1 So this would be
Well, this is technically two connected. Actually, this is the
有
only
一些
one.
奇怪的图形，像这，
No. So this is a two cut set.
Oh, we
You
want it
don't
to
need
be
that
3.
one.
这是一，
Yeah,
它也是一个。
Okay.
我知道怎么样证明这
And
个
of course, I'm writing pen. So.
That's okay. I just need to give you mine, not yours. So we need to bucket all 3 of these. So we just don't want them, so they can't be connected to each other.
这个绿茶跟国内的绿茶是一样的，
Well, I guess not.
并不
Go ahead.
Because if we did 2 and 1, 2, 1, 2, yep. And 1, and let's say 2.
可以小。
So if
下
we
面
remove
我
these
操你
3.
的机会我就
Yep, now you're disconnected. Yep.
Okay.
And you need all three to be
无糖。
Yes, and here we would need these
还有
3.
那
right.
天哪，
So that's one case.
Okay, how do you know?
Oh, okay, so you're ahead of us, but when you say this includes the complete graph,
Like, what would I be
so
saying? Okay.
if the min degree is n minus
Fill in
1,
that blank.
So I guess
Yeah.
here,
Have the
what we did in the past. was
so there's only 2
consider
cases. It's either n minus 1, which would be
How
complete,
the edges were in the cuts,
or
right? Because
the
here
min
you
degree
can
is
just
greater than or equal
flip
to n
these back
minus
and
2.
forth, they're all separate.
Yeah, so in this case, there are no edges in the cut set.
Right.
So that would be my case.
So remember connectivity means we're going to remove vertices and
We
leave
actually,
an
we just saw
isolated
the two
vertex.
edges in the cut set.
够坏。
Yes. So this is the 1 edge.
No, right, yeah, and the complete graph. For consistency, the connectivity of a complete graph is n minus 1.
这够坏。
So
So you know we only left a single vertex.
Where
Okay.
one vertex is connected to only one side, that's kind of a red flag because
可以啊，当我们知道 k 你只要说当 k 小于等于2的时候，
Hey, make it out.
So in this case,
What do you, tell me something you've tried,
in-
whether it worked or not.
because deleting this edge doesn't,
Disconnect.
right, so the disconnecting happens with these two vertices. So if I delete
Well,
this,
we started by just kind of writing out all the
and that's an
inequalities.
observation to you.
So kappa less than kappa prime,
Okay, so.
I guess less than or equal to,
Kappa less than or equal to kappa prime.
yeah, less than or equal to small delta,
Small delta,
Well, it's maximum.
and that's less than or equal to big delta,
which is less than or equal to big delta,
Still,
and that's less than or equal to 3.
less than or equal to 3.
So we said, you just break it up into some cases. If kappa is 0, 1, 2, or 3,
so
Okay.
we know that 2H
tackle them
doesn't
each
work
one
in
by
that
one.
set.
Okay?
Some of them were pretty easy.
Okay, which will give me an easy one.
So if kappa is 0,
Kappa is 0, right?
then the graph is disconnected,
Okay?
and then kappa prime is 0,
And kappa prime is 0,
and we're done.
and we're done, okay?
Same thing if kappa is 3. It's about that simple.
If kappa is, what happens?
Well, if kappa is 3, then all of those numbers have to be 3.
Then all of those numbers have to be.
And then
okay,
kappa prime equals kappa.
prime.
Yeah.
Okay, so you're left with 1 and 2.
Yep.
Okay.
And so we drew a picture, which was hardly a proof, but the picture made it kind of clear.
Okay?
So if kappa is 1, let's say, then we've got.
Okay, so the vertex connectivity is 1, meaning I'm going to break this up into at least 2 components, maybe 3.
Right.
Okay?
And then that vertex in the middle has a maximum degree of 3.
Has maximum degree 3.
So by the pigeonhole
By
principle.
the pigeonhole principle, what's the pigeonhole principle?
You have at most 3, so this is
I have n pigeons flying into k holes, then some hole has n over k, integer part of n over k. So I have 3 pigeons. What do the pigeons correspond to in this case?
The edges.
Edges. We know that this vertex has degree 3 at most.
Mhm.
So I have 3 pigeons flying into 2 holes. One has to have 2, it's a connected graph, so, and the other one has to have 1. So the vertex connectivity, well, clearly, what's the vertex connectivity? 1, which one? The one in the middle, I remove the one in the middle that disconnects the graph. Edge connectivity,
Edge in the cut side. Can't have an edge in the cut side. I can't have more edges than one in the cut side, so this is really all the twos.
which one?
This is my ones, this is my twos.
What middle
3
one?
was just smoking.
This edge. Okay, so if I remove this edge, it disconnects the graph. Okay, so it has edge connectivity 1, vertex connectivity 1, so we're in good shape. The next one is the hard one. Okay, so we've got 0, 1, and 3 are taken care of, so the next one is 2 vertices. Disconnect the graph. Now what?
Similar picture with both of those.
By the way, vertex connectivity is 2. So this is connectivity 2. Okay? What's the degree of these points?
At most 3.
At most 3.
So, similar picture to this other one. They're each going to be connected to at least one component by at most one edge.
Okay, so if they each go to one component, if they each go like this, so we got 3 edges split among 2 components. It could have a third component and then everything's easy. But we have these 2 vertices sending out 3 edges which go to these 2 components. Then one must send one way and each one must send 1 in one of the 2 directions. If both ones go in the same direction, then the connectivity is 2, right? So I would remove these 2 edges and we'd be done. So maybe the only hard part is if this goes this like this, and this one goes like this, and we have degree 3. Now what do we do? This looks hard. But by the way, can you remove two vertices and disconnect the graph?
Yes.
Can you remove two edges and disconnect the graph?
Yes.
Oh, maybe it's not so hard. We'll put two edges.
The two singles.
Okay, so this edge and this edge. Okay, next, that's it. Okay? Is that clear? Okay, so sometimes it takes a little more arguing than others, but,
It does.
and can it be three connected?
Could,
Do we
could
have
be.
to show on the two, a possibility where the two vertices in the center are connected to each other? Or no?
Yeah, so, I mean, we really, of course, so the question is, if the two vertices that disconnected are like this,
Yeah,
and then, so they have degree 3, so it could go like this, and like this, and like this, and like this, which is a little problematic. Is that problematic? What happens in this case?
okay, it's two. It still works.
It still works, because the edge connectivity is,
Two.
the edge, which two do I remove?
The, yeah.
And which two vertices do I remove?
In the center.
The two.
不可能的三十。
Very good. Okay, do I have to show 3? Show that, can it be 3 connected? Well, if it's 3 connected, then its edge connectivity is 3, and its min degree is 3, so we're done. Min degree, max degree.
Because of the
Okay.
inequality.
All right, number 3, let G be a graph of at least 3 vertices if the min degree is n minus 2. So if the min degree is n minus 2, what can you tell me about how many vertices does every vertex miss? At most. Okay, min degree is n minus 2. We have a graph on n vertices. Min degree is n minus 2. Then at most, every vertex misses how many vertices? 2? One. Okay, because we don't count itself. Okay, so we know that it goes to at least n minus 2, so it misses at most 1. So the connectivity is equal to the min degree. Okay, this was number 2. Number 3. This is a graph of order n. So I claim that there's really just 2 cases. The min degree is equal to n minus 1. If the min degree is equal to n minus 1, then what does the graph look like? By the way, this is a graph of order n. It's complete. And the edge connectivity, we remove n minus 1 edges from any one vertex. And the vertex connectivity is, I'll leave a singleton, I'll leave a single vertex by removing any n minus 1 vertices. So not only do I know that it's greater than or equal to n minus 2, I know that it's exactly equal to n minus 2. So min degree is exactly equal to n minus 2.
是有可能
We're
是
going to assume that
exactly
one degree
degree
and
in
minus one, then it's a complete graph.
Right.
So, so that means the vertex connectivity is
And also
We'll
n
remove
minus
the
1.
edge.
So you're gonna remove vertices until you only get a singleton left.
so all but one.
So n minus 1. And then, and if the min degree is n minus 1, we're gonna remove all those edges. N minus 1 edges.
然后
But then that's not a
所有人
contradiction.
如果他不知道你懂
We're trying to show that they're equal, right?
Having an isolated vertex after removing stuff is the
That-
same as
So,
disconnected for,
so by definition, we say that the connectivity of Kn is n minus 1. So if I have min degree n minus 1, I disconnect the graph by removing n minus 1 edges, and I disconnect the graph by leaving a singleton, so they're both n minus 1.
Okay. So why do we have to do that when this is the direction? It says show that if the minimum degree is greater than or equal to n minus 2, then or equal to each other.
that's one case. Right, the other case is equal to n minus 2. There's two possibilities,
But it
right?
这里以外，他还看到一条线或者一个直
So,
But this is saying it has to, it only works up to the minimum degree.
right, so there's two things that the minimum degree can be. If it's bigger than or equal to n minus 2. So it's n minus 1 or n minus 2. What we just did was the n minus 1 case.
And it worked.
And it worked. So n minus 2 is what, we gotta think about now.
So now, second case.
为什么 complete graph 加上一个点？
It's not complete. Vertex connectivity
So,
would be n minus 2.
are you
如
sure
果
that
点有意义啊，你用这个点你能找啥？
So that's what you gotta do. So the idea is you,
这个点的底部是 n 减
well, if you have n minus 2 vertices in this cut set, and then you have two sets that can be divisible,
n 减2有一个点
and your max degree, or your minimum degree is n minus 2, then you're definitely connected to all of them. This is n minus 2 as well, so it's possible to have an n minus 2 cut set with n minus 2 max degree. And the center, each of these has degree, so maybe this is complete, so then each one of these has degree n minus 3 in here. And then since they're connected to each of these, then they're n
能
minus
干嘛呀？什么干不了？什么说不了？
or n minus 1. So you could have totally complete here and then two edges on the outside. Right? So you have an n minus 2, k n minus 2.
我只有这一道法。
And then you add two vertices connected to everybody.
我希望能有一个特大，就是未来是个像什么系统，
So the min degree in here
是会有点难。
is n minus 1 because you had n minus 3 and then you added 2. Which is at least n minus 2. So that's fine.
你说啥？因为不知道还有很多
But
其他的话好像
Okay, how we doing?
So this is a graph.
然后胜负
What we want is a graph that's n minus 1 connected
What should we do?
它是
for a contradiction maybe. We want n minus 1 connected and
Min degree is
统计 program。
min degree
greater than or equal to n minus 2.
n minus 2.
And again, I've done the easy case. If the min degree is n minus 1, if the min degree is n minus 1, it's a graph on order n, then what's the graph? The complete graph. And the result follows. Then the min degree is equal to, sorry, the connectivity is equal to the min degree, n minus
It's
1,
possible
and
that this is connected to
we don't
all
have to
of
do
those
anything
two
else.
here.
So here I have that the min degree is at least n minus 2, so in fact the min degree is exactly equal to n minus 2.
对对对对。
It's not n minus 1 connected because you can delete all the neighbors of this guy. Does that make sense? It's kind of,
So what do I need to show? What do you need to show?
need to think about that.
好像都是这样，不对。
I'm following it 100%.
So I want to show that the connectivity, to separate this, to disconnect this graph, I got to remove
太阳和头电。
n minus 2 edges. Okay, so let's see, I've got I have two independent vertices. I know the graph is not complete. We know that the graph is not complete. So what if I remove all these vertices? Does that disconnect the graph? Okay, one more time. I know the graph is not complete, so there are two vertices that are non-adjacent to each other. So here are n minus 2 vertices that leave a disconnected graph. Okay, what else do I need to show now? I need to show that that's the smallest. Okay, so what do I have to use? I have that the min degree is at least n minus 2. So what can I do? So suppose I take 3 vertices. Sorry, take n minus 3. Let's just look at n minus 3 vertices. So what can you tell me about, and there are 3 vertices left. So what could the graph look like? Notice the graph has min degree n minus 2. So among those 3 vertices, what can you tell me about amongst, let me put it in a different way. This vertex could be adjacent to all these n minus 3, but the min degree is n minus 2. So how many edges must this vertex have amongst these 3? At least. Okay, what about this one? And what about this one? Okay, so this one has degree at least 1. This one has degree at least 1. So I'm going to put it in. So there's an edge. And I'm just worrying about here because I'm trying to show that this is connected. This one has degree at least 1. Where could it go? It either goes here, or both. So in fact, that doesn't disconnect the graph. Okay. So when we have high degree, it's kind of a nice way to look at this. What about when the min degree is n minus 4, right? Does he ask that next? Oh, sorry. What about when the min degree is n minus 3? When the min degree is n minus 3. So if the min degree is n minus 3, let's generalize this. So I'm going to take n minus 4 vertices here. And this is, let's imagine that this is complete. That's complete. Now I've got 4 vertices left. We'd like it not to be complete. We'd like it to not be complete. So what if I put those 2 edges in, and I put all these edges in? What's the min degree of this graph? So let's see, n minus, so the min degree of this graph, this vertex is adjacent to n minus 4. It has degree n minus 3. And, they all have degree n minus 3. But in fact, when I remove these n minus 4 vertices, it disconnects the graph. Okay, so if I go down even one more, then I have a graph that contradicts this. So if the min degree is equal to n minus 3, we've got a problem. Okay? All right, so I'm going to leave 4, 5, 6. Again, you might want to look at, 7. Sorry, let's take a quick look at 7. Is there a relationship amongst the connectivity of G plus H, the connectivity of G, and the connectivity of H? So remind me, what is G plus H?
Is that just the unions of the vertex and edge sets?
So he defines this. G plus H is where I'm going to take these two sets and I'm going to put all the edges between them. Let's see. Where does he define G plus H? So I have a copy of G. I have a copy of G, and I have a copy of H, and I put all these edges in. I think that's G plus H.
Everything in G is connected to everything in H?
Everything in G is connected to everything in H.
Okay.
So what can you tell me about the connectivity? One more time. I'm looking at this new graph, G plus H. So I take a copy of G and a copy of H, and I put all the edges in between G and H.
What does that mean in graph?
Isomorphic.
I think you'd have to remove one entire graph, and then some to disconnect it, right?
Okay, so let's see if we believe that. If I don't remove all of G or all of H, if I don't remove all the vertices in G or all the vertices in H, then I'm going to, let's say I leave one vertex in H, it's adjacent to everything in G, the remaining graph has got to be connected. So I'm going to have to remove all of G or all of H to have any chance of disconnecting this graph. Okay, so imagine I remove all of G. If H is connected, then what are we going to do?
Remove K.
Remove. If H is K connected, if H is K connected,
Remove G plus minus 1.
Okay, so in fact, what I'll do is I'll remove all of G. So the connectivity of G, it's just plus, right? G plus H is equal to the minimum, so it's the smallest of the order of G, the order of the vertex set of G. Let's try and write G, plus the connectivity of H, or the order of the vertex set of H, plus the connectivity of G. So it's the smallest of those two values. Okay, removing one piece or the other will leave just one of these. If I don't remove all of these, the whole graph is connected. If I don't remove all of G, then what remains will be connected through a vertex in G. So I have to remove all of G and then disconnect H. Or I have to remove all of H and disconnect G. So it's the minimum of those two values. Okay, and now that you know that, you can go back and actually do A, B, and C pretty easily. Okay, not right now. We'll save that for for Thursday. Okay, so now what I want to go a little bit further, and so I don't want to necessarily talk about a disconnecting set, although that's one of the things that we will need, but so we'll talk about a separating set. So if I have a graph G, a separating set, what do you think a separating set is? By the way, this is on page 246. So I'm going to take 2 points, a UV separating set in G is a set of vertices and that separates U and V. So imagine that I'm going to choose 2 vertices U and V, and I want to do this probably optimally, but that's not crucial. I take a set S. Then when I remove the set S and all the appropriate edges that come out of S, then there's no path from U to V. So I separate U from V. Now, I'd like to probably do this in some optimal way, so we might ask for minimal separating sets. So I want to separate U from V by sort of removing the smallest number of vertices possible. So that's a minimal separating set. Okay, and there's no smaller. Let's imagine my picture that S is the smallest. That S is a smallest set that separates U and V. So one more time, when I remove S, the vertices at S, then there's no path from U to V. Then, in fact, what I know is that there are, let's see, I'm gonna say, let's call the order of S little s. Then I'd like to know, in the big graph, remember this is part of a big graph. So in the big graph G, I'd like to know how many paths there are, how many disjoint paths there are from U to V. Now notice, once I remove this set, then U and V have no paths between them. So what's the greatest number of paths between U and V? Sorry, the greatest number of disjoint paths, vertex disjoint paths between U and V. Do what? Little s. So we can imagine that if this is the smallest separating set, if S is the smallest set that separates U from V, then we can imagine that there are these paths that are vertex disjoint. Vertex disjoint. Oh, that's interesting. So I've got S vertex disjoint paths. Sorry, Yeah, S, vertex disjoint paths from U to V. So in fact, that tells me a lot about the connectivity or vice versa. If I know that the graph has connectivity K, then we know that I can find this set of K vertices that disconnects U and V, and I'll find these disjoint paths from U to V. So there's a relationship between the number of and we're going to use some fancy notation. These are internally disjoint. These are internally disjoint paths. Okay, so because they're not disjoint paths, right? They go from U to V, and they have some overlap. Every two of these paths have an overlap. What was that? U and V. Okay, but internally to these paths, once I get inside the path, internal to the path, there is nothing on this path that's internal to this path, which is internal to this path and internal to this path. So the smallest number of internally disjoint paths, the largest number of internally disjoint paths between U and V relates to the connectivity, relates to how many vertices I need to disconnect this graph. And that's essentially Menger's theorem, which I did mention Menger, which is at the bottom of page 246. G is a connected graph. If it's not connected, then it's no fun, right? Then there's no reason. If it's not connected, then you don't have to do anything to disconnect the graph. Okay, if I take any two non-adjacent vertices, it's important we take non-adjacent ones, then the minimum number of vertices separating, in other words, the smallest number of vertices that cut U from V, the minimum number of vertices, like this set right here, the minimum number of vertices that disconnect U from V is precisely equal to the minimum number of disjoint paths that start at U and end at V. And that's Menger's theorem. Now that's a big leap. That's a big leap from going from the vertices that disconnect U from V and this number of paths. Okay, so there's this relationship between the number of vertices that I need to remove to disconnect U and V and the number of internally disjoint paths. So just to give you one example, if we look at 6.4.2, so on page 247. So notice U and V, between U and there's the graph on top. A is the graph. B is the graph with 4 paths from U to V designated. 4 internally disjoint paths. The only place they overlap is at U and V. Notice path 1 goes through this dotted circle up here. Path 2 goes through the second dotted circle. Path 3 goes through this third dotted circle. And path 4 goes through the fourth dotted circle. Everybody sees those dotted circles. Okay? So I have 4 internally disjoint paths. Now, can you give me a set of vertices that disconnect U and V? Say the dotted vertices. Okay, the ones with the dotted circles. If you remove those 4 vertices, notice they're on all of these disjoint paths. If you remove all 4 of those vertices, then we've disconnected U from V. So there's this relationship between the number of internally disjoint paths from U to V and the number of vertices it takes to disconnect U from V. Now it's related to the connectivity of the graph, but really we're now being much more specific. We're saying that we can disconnect 2 vertices. It doesn't say anything necessarily about the connectivity of the whole graph. Okay? All right, so we'll end there I did want to talk a little bit more about Megners theorem, but we'll talk a little bit more about connectivity and edge connectivity on Thursday, and then I want to start with independence. So chapter 7, if you read through section 7.1, independence and matchings. One really important example in applying graph theory or some of the algorithms is, imagine that here's one of my favorite examples. So I have potential medical school students. Okay, so here they are. And potential, these are medical schools. Med schools. And this is really, they really use an algorithm for using this idea of matchings and graphs. The potential medical schools, everybody wants to go to Harvard and Yale, and but somebody's got to end up at CU, I guess, is here. I mean, not only guess. All the medical schools are here. So how do we sort of maximize? There's a shortage of doctors. So how do we maximize the number of students that are going to places that they want to go to? Okay, and medical schools and the Medical School Society actually uses an algorithm to match up the potential medical schools with the medical school students. So there's a ranking. The medical schools give a ranking of the students. The medical schools give a ranking of the students. The students rank the schools, and then they try and get as close as possible of giving each student a high ranking and being sure that each student gets a school. Sometimes that doesn't work, and sometimes you don't get admitted to medical school. Okay, but this really exists. That this is algorithmic. They actually do this, and they find what's called a matching of the medical school students to the medical schools. Okay, and in this case, it's really more than a matching, because a medical school might have a class of 15. So in fact, there might be 15 potential medical school students that are matched up with Harvard. Okay. So it's a little bit more than just one edge, because there are more potential medical school students than there are medical schools. Okay, and we'll talk a little bit about that on Thursday. Test is a week from Thursday, right?
Yeah.
Oh, and it's hard. See you Thursday.
我家里头学些什么呢？Math Clinic。